Hello, students. This is Tim Tomlanovich. Hope you're doing well. This is Learning Plan 3 lecture notes. Our course competency is Analyze Concrete Mix Design, course competency 4. Okay, so with that, I'm going to get my laser point out here. So now that we're done understanding aggregate properties, now let's talk about concrete. All right, so our learning objectives in this learning plan is we're going to define Portland cement concrete PCC ingredients. So Portland, that's a capital P because that's a brand name. So PCC. So if you hear me say PCC, just remember Portland cement concrete. And we're going to discuss PCC, Portland cement concrete properties in this learning plan. All right, so you have seen this before. Okay, so let's do this little video here. Let me. So hopefully you can hear that. So I'm just going to play that again. Okay. So Portland cement concrete up to 8% air, 7 to 15% cement, 60 to 75% are aggregates, and then 14 to 21% is water. Okay. So we have three ingredients: cement, water, and aggregates. All right, so PCC is a mixture of two main components. They call it paste, which is 25 to 40%, and aggregate, 60 to 40%. So paste is the glue that binds the aggregate together. Portland cement. So paste includes Portland cement, water, and entrapped air or entrained air. Okay. So paste is the Portland cement and water. So those two of the three ingredients, they call it paste. Okay. And then the entrapped air and entrained air is an admixture. All right, so the quality of concrete depends greatly on the quality of the paste. Each particle should be coated with paste and all spaces between particles filled with paste. So the quality of the paste, I picture this as making pancakes. What happens when we have too little water when you're trying to make pancakes? One, your pancake mixture is not mixed very well, okay? And then it's really clumpy and it's not coating properly. So, but on the other hand, if my paste is, your pancake mix is too runny, right? The pancake mix is pretty much self-leveling. It gets diluted, okay? It gets diluted. All right. Calcium silicates in the Portland cement reacts with water, so they call that hydration, to form the hardened cement paste mass. Okay, so as soon as water or humidity in the air touches Portland cement, it'll start hydrating. So they call that process curing. So I like this one. This is a nice video here. It kind of shows the. Let me get rid of this guy. So this is cement hydrating. So as you can see here, these are the cement particles, and this is the water in there. And as it hydrates, you'll see that this will, as you can see, as the cement hydrates, these are the pores. This is the water in there. Okay. And you see over time, as the cement sucks up the water to hydrate, we get less and less voids and less water. So this is why we don't want to have too much water, because we'll have leftover water in there, and then we'll get shrinkage, and our cement is diluted. So I thought this is kind of a neat little. So this is 30 hours. So look how small that is. 0.275 microns. So that's really small. So as you can see, the water is disappearing. It's hydrating into the cement. So and then in the cement. So when okay, it's a chemical reaction. So there we go. So over time, you can see this is what you want your cement to look like. Okay. All right. So Portland cement ingredients: calcium. The main Portland cement ingredients are calcium, iron, silica, alumina, and sulfate. So where do we get all these? Bedrock. We get those all from bedrock. I found this online, so sometimes they call it magnesia, another one, silica, alumina, calcium sulfate is another one, lime, right? Lime is another one. Okay. All right. So here's another video. Oops. Okay. All right. So Portland cement raw materials are ground in a wet or dry process. It's heated in a kiln at 2,600 degrees Fahrenheit to 3,000 degrees Fahrenheit to produce clinker. This is clinker right up here. Okay. Right here is clinker. Okay. Clinker is then ground with gypsum. The reason why gypsum is added is it has to slow down the hydration rate. Otherwise, it will cure, hydrate so fast we won't have time to work with it. So people think asphalt. When you go buy asphalt, where they're paving a road with asphalt, asphalt's about 212 degrees Fahrenheit. Okay, so it does look hot and smelly and stinky. But believe it or not, the production of cement actually creates more CO2 emissions than asphalt, because we have to heat these bedrock and soil products at 2,600 degrees Fahrenheit. As we're only producing, warming up asphalt at about 200 degrees Fahrenheit. Okay, so there is actually a lot more CO2 from the production of cement. So here's another videos. Okay, Portland cement physical properties. All right, fineness. So basically, that's how fine it is ground. So the more finer it is, the faster it'll hydrate. So strength of it. So actually, they make strength specimens of just pure cement, Portland cement, and then they'll crush it to see how strong it is. Heat of hydration. So that's how fast it'll cure, and then setting time. So this is why they add the gypsum. They have to add gypsum is to slow down the setting time. Otherwise, literally, there will be no time from it to go from the concrete truck to the site, because it'll set already. So they need to slow that down. Okay. So there's 5 different types of Portland cement. Okay. Type 1 is normal. That's the stuff you normally buy at Fleet Farm, Menards, Home Depot. Okay, you'll see that in the bags. Okay. Type 2 is moderate sulfate resistance. Why do we want moderate sulfate resistance? Sulfates will actually corrode concrete and reinforcement. Okay, our soils around here in Wisconsin and a lot of areas in northern parts of the United States have sulfates in the soil. So when a footing is actually sitting on the soils, when the groundwater gets saturated, it'll actually start corroding things. So what they do is they'll use type 2 moderate sulfate resistance. So a lot of times what you'll see a type 1 / type 2 Portland cement bag, which is 94 pounds. Okay, a lot of times you may see that in Menards or Home Depot. Okay, so they also make type 3, which is a high early strength. So in the winter times, we want to get our strength early so we can keep constructing so it doesn't freeze. Type 4 is low heat of hydration. Typically, where you'll see this type 4 is when you're constructing a large dam or mass concrete. We want to slow down that heat of hydration because the more mass there is, the more heat's going to be produced, and then we're going to get cracking and it's going to cure too fast. So we need to lower that heat down. And then type 5 is high sulfate resistance. So where you typically see type 5 cement is in wastewater treatment plants and concrete sewer pipes, okay? Because of the sulfates from human waste and stuff, it'll severely corrode that. So we need type 5, okay? So another way, instead of actually, these are very expensive to produce, these last three, okay? So sometimes what we'll do to create a type 3 is we'll use a type 1 and a type 2, and we'll add an admixture, a chemical admixture to make it a type 3. And the same thing, we can add a retarder to make it a type 4 to slow down the heat of hydration. Actually add a liquid admixtures to make a type 4. To physically grind these and produce these is very expensive, so it's a lot cheaper for us to add admixtures, except, so type so unless it's a specific project. Okay. All right. Here's another video. All right, mixing water. So basically, mixing water may have impurities that can affect the concrete. So typically, potable water is basically acceptable. Okay. However, sometimes there's chloride. So there's a lot of chlorine in our city water. And I've been on a project where the specs called for no chlorine in water because chlorine can actually corrode steel. Okay. Sulfates can cause expansive reactions. Alkalis affect setting time and strength, and organics can reduce setting time and strength. So depending on sometimes we'll have to do a chemical analysis of the mixing water to make sure some of these aren't causing this. So a lot of times you don't see this immediately, but over time we can see these. So these would all be in the water. Okay, so mixing water basically should be potable. Okay. All right, let's talk about entrapped and entrained air content. Entrapped air is air introduced through the mixing process. So when you mix anything, you produce air bubbles. That's what happens. Entrained air is intentionally introduced to protect concrete from freeze thaw. So air content typically ranges between 1.5%. So this is only entrapped air, all the way up to 8% when we have entrapped and entrained air, depending on the aggregate size and exposure level. So just keep in mind as air content reduces the strength of the concrete. So it's producing actual mini tiny air bubbles in the concrete, okay? So what that is doing is creating air voids in there and places for water to go to expand, okay? So if we're producing millions and millions of little air bubbles, right, what are we doing? We're actually pushing the aggregates apart, okay? Because we want aggregate on aggregate contacts and, for friction, okay? So if I look here, so if we have the same volume on this picture on the right, so if our air goes up, something else has to go down, okay? So, and then we have non-entrained air, or as our air goes down, we have something else increases, so probably most likely more aggregate, okay? So just keep that in mind. That's why we want to stay within no more than 8%. Okay, because as soon as we get over that, we really start seeing some massive strength decrease in concrete. So between here and here, usually about 7% is where we like to be in northern climates. That produces millions and millions of air bubbles. So when concrete gets wet or saturated because it's permeable, there's room for the water to expand and it won't break apart the concrete. All right, let's talk about the water cement ratio, W over C. Literally, it's a mathematical function. Water divided by cement. Weight of water divided by weight of cement. So the quality of hardened concrete is determined by the amount of water used in relation to the amount of cement. Water cement ratio. The water cement ratio is equal to the weight of water per cubic yard divided by the cement weight per cubic yard. So when we do mix design, we're always doing it on a per cubic yard basis, and then we'll cut it down to cubic foot basis. Okay, so I kind of like this picture here, a low cement ratio. See what's happening here? Our cement particles are closer together. It's kind of like that pancake analogy I did. So as soon as our water cement ratio increases, so all of a sudden we're going to dilute it. We're going to dilute it. So if we don't add any more cement but keep adding water, what happens? We have more water than we have to cure our cement. So we get a weaker mixture, and we creates voids, and we get more permeable issues. Okay. So in concrete, the lower the water cement ratio, the better. Lower the water. Not want to increase. All right, advantages of reducing the water cement ratio: increase compressive strength, okay, lower permeability and absorption. So if you look here, lower permeability, right? If we have too much water, we have all these voids. The water can get through there easier. So if we have this all nice and tight, okay, the water can't get through there as easy. And we increase the strength because the cement was properly cured and there's no excess water in there, and our aggregates are touching. Increased resistance to weathering basically makes it stronger. The freeze thaw action typically. Better bond to reinforcement. So water does not bond to reinforcement, so the more water we have, the weaker it's going to be. Less volume change from wetting and drying. Okay, so if there's cavities in there, so when things get wet and they dry, they actually change shape. They expand and contract. So if we have less water, that'll allow us not to happen. And reduce shrinkage cracking. So what happens when water evaporates over time? This takes many years. That concrete will actually shrink and create cracks. So this is an important thing, why we want to keep the water cement ratio low. Weight of water divided by weight of cement on a per cubic yard basis. Okay. So we already know the aggregate properties. Okay. So you want to know those. Make sure you understand those. Okay. All right. Let's talk about aggregate moisture conditions. Remember this part again? So oven dry, no moisture within or on the aggregate. Okay. Saturated surface dry. The surface of the aggregate particle is dry while the pores of the aggregate are filled with water. And then wet, the pores of the aggregate are filled with water and there's free moisture on the surface particle. Okay. So let's talk about this. How does the water cement ratio, WC, change of each aggregate moisture condition? Okay, so let's do some scenarios here. So our aggregates are dry, oven dry, which is never going to happen in the concrete world because our aggregate stockpiles are always outside. So if I have a given amount of cement and a given amount of water, so let's do a pen. So water, cement equals. So say we have 100 pounds of cement on a per cubic basis, and okay, so this is the variable that's going to change the water. All right, so if I have a dry aggregate, so basically what's going to happen when, say, I need 50 pounds of water per 100 pounds of cement. So what's my ratio? That is 0.50 water cement ratio, right? All right, my aggregates are oven dry. So we need 50 pounds of water to properly hydrate that cement. So, but before that 50 pounds of water, some of that water is going to be sucked inside of the pores. Would you agree? I agree. So what that means is that there will be less mixing water, okay, because some of the 50 pounds was sucked into the aggregate. So now we may have 30 pounds of water available to hydrate the cement. So what does that do to the water cement ratio? It decreases it. So it's this answer right here, okay? It decreases it, all right? So that could be bad because then we don't have enough water to hydrate our cement and our bond is going to be weak, okay? Now let's move to saturated surface dry, okay? All right, our aggregate is saturated surface dry. That means, right, all the pores are already filled with water, and then when we add our mixing water, there's not going to be any excess water, or none of that water is going to be sucked up by the aggregate. So that means our water cement ratio stays at 0.50. So what happens to our water cement ratio? It stays the same. We're at the equals the water cement ratio. Okay, now let's go to the wet condition. Our aggregate pores are filled and we have excess water on there. Okay, so what happens to the water cement ratio? So now we have excess water plus we added 50 pounds. So now we go up to 80 pounds of water because we have all this excess water. It rained all night. So what's going to happen? 80 divided by 100, our water cement ratio goes up, and we do not want that to happen. Okay, so we'll in the next learning plan we're going to talk about how do we take into account these three conditions. Okay, so it's just something to keep in mind. So especially when it's wet. So when our aggregates are wet, or if you add water to the concrete, we're increasing the water cement ratio. Increasing goes up. The water cement ratio goes up. That means we're decreasing the quality of the concrete. Okay. So, oh my, that's a lot of information. So I'm going to keep going. So you can take a break if you need a little break. All right, let's talk about admixtures. Ingredients in concrete other than cement, water, and aggregates that are added before or during mixing. Okay? Cement and water, remember that's the term paste. All right, so what we do is we add admixtures to reduce the cost of concrete construction, achieve certain properties of concrete, ensure quality concrete during mixing, transporting, placing, and carrying, and overcome emergencies when placing concrete. Okay? So this is why we need to add admixtures. So we have air entrainment. Okay, remember we talked about that? Tiny little million air bubbles in there for freeze thaw. Water reducing, retarding, okay, accelerating, super plasticizers, and mineral. We'll go over each of these. Okay, mineral, mineral. So this is literally they're chemicals, or sometimes there's mineral. properties. Okay, so all right, so let's go over this video. All right. Water reducing admixtures used to reduce the quantity of mixing water required to produce a certain slump and decrease the water cement ratio. Okay, so we say we want a water cement ratio of zero point 0.5. Okay, um, but what we want to do is we want to be able to make the concrete the consistency so it's easier to work with. So what we want to do to make it more easily to work with, we'll put a water reducing admixture. Okay, and that'll make so that eliminates us adding more water, which increases the water cement ratio, which we don't want. But it'll also help reduce the amount of water we need, right? Because we're adding this admixture, which makes the concrete more workable, the consistency. Okay, so we're not affecting the quality of the concrete. So that's what a water reducing admixture does. Okay, there's another video. Okay, retarding admixture. Use to retard the rate of setting, used in hot weather situations and or difficult placement situations. Okay, look at this. Look at all that concrete there. Holy, or the reinforcement there, pretty tight there. Accelerating admixtures. Used to increase the rate of setting, used in cold weather situations or when early concrete strength is required. Okay, so there we got there, and then super plasticizing. They call these high range water reducers used to bring low slump concrete to high slump without adding water. So it's also a water reducer, it's just a little bit different kind. Okay. So literally it helps make the concrete more fluid to get it in between the reinforcements. Okay. Retarding hot weather, accelerating cold weather, superplasticizing, or water reducers help make the concrete more fluid for easily placed without affecting the water cement ratio. We want to keep the water cement ratio because a lot of contractors will do is say, "Oh, that concrete's too stiff. I want to make it more fluid to make it easier to work with." They'll add water. Okay, that's diluting the cement. We're increasing the water cement ratio. We're decreasing the quality of our concrete. We do not want to do that. So that's why you want to use super plasticizers or water reducers. Okay, let's talk about mineral admixtures. Powdered to pulverized mineral materials used to change the properties of plastic and hardened concrete. So cementitious, hydraulic cementing properties, natural cement, so recycled cement, blast furnace slag, and hydrated lime. So believe it or not, it'll actually create a cement-like substance. Okay, so cementitious. Okay. Pozzolanic, materials that possess little or no cementing value alone, but react with cement and water to form cementitious properties. Fly ash and silica fume. Okay, so typically coal-fired power plants they can create that's the by so fly ash is a byproduct of burning coal. So what we're able to do is be able to use some of that fly ash, and it's a pozzolanic material. As long as it meets a certain spec and certain property, we can replace the cementitious material, the pure Portland cement, with some fly ash, and we'll actually get the same property. Okay, so what is that doing? Because it costs a lot of energy to make the clinker and the cement. So if we can start replacing with this, we're actually reducing emissions into CO2 emissions. Okay, the last one of mineral admixtures is inert, have no cementitious or pozzolanic properties, are usually used to improve workability. Pulverized limestone, dolomite, and granite. Okay, so the kinds of admixtures. All right. Going to keep on trucking here. So a lot of information on this. All right. Testing freshly mixed concrete. So this is what you are going to be doing, and I'm going to offer you the ACI certification. So typically we're going to measure temperature, slump, air content, unit weight, yield, density, and strength test specimens. Okay. This is typically what we test to um, determine the quality of our concrete. So temperature, obviously, is it too hot, too cold? Slump, that measures the consistency, air content, number of microscopic air bubbles, unit weight. Concrete should have a certain unit weight, and then we got to see how strong they are. We'll make cylinders and beams. Okay. All right. Okay. Okay. So again, we are going to go, there's standards that we're going to do all of these. Okay. So don't worry, you will do all of these to understand what each of these tests do and why we need to measure them. Okay. For the quality of the concrete. All right. So how do we test concrete? Test hardened cured concrete. So we use compressive strength. Okay. Compressive strength cylinders. And then we also do flexural strength for beams. Okay. So you remember, so when you look at a bridge overpass, those concrete beams, there's reinforcement in there. Concrete is weak in tension and strong in compression. So basically, what we knew when we break concrete, we call it a modulus of rupture. That value will determine how much reinforcement we need to get into there. So when the concrete will always crack in tension. It always cracks, but we control the cracking. So we need to crack the concrete so we can engage the reinforcement. Okay, so that's why we make beams, especially in DOT roadways. And then typical is we also want to know the compressive strength when we're trying to squish it. So think about that high-rise building that is one of Sears Tower, John Hancock building, the Burj Khalifa. So basically there's a lot of weight sitting on that cylinder. So we want to make sure we get proper compressive strength. All right, so what do we do? So typically a compressive strength is typically comprised of 2 or 3 cylinders at 23 days cured in the lab conditions. Okay? The results of the temperature, slump, and air content must accommodate the results of the cylinder testing. Typically sets of 4 6-inch diameter by 12-inch cylinders or 5 4-inch by 8-inch cylinders are molded when testing freshly mixed concrete. Okay. One cylinder is tested at 7 days. In 7 days, we should get approximately 2/3 of our design strength. Okay. Two 6 by 12s or three 4 by 8s are tested at 28 days. So the average of the test must meet or exceed the design strength. And then our last cylinder is a spare cylinder. So when we talk about design strength, we design concrete to make its design strength. You hear 4,000 pounds per square inch, 4,000 psi, pounds per square inch concrete. It needs to achieve that strength in 28 days. Okay. All right. So by knowing if we're going to get 4,000 psi in 28 days, we have a good gauge in 7 days that it's going to be okay. What happens if we don't make the 4,000 psi in 28 days? That's why we have a spare. So sometimes we have to um, let this cure longer to see if we make it. Okay. So by having the temperature, slump, and air content, we can know if our cylinders aren't making strength. We can do some reverse engineering with the slump, air content, and temperature to see kind of problem solve to see what is happening with the cylinder. Okay. So these are lab. So these are lab cylinders, and we'll talk about field cures either this lesson or when we're actually um, testing concrete. Okay. All right. Concrete strength factors. So number concrete now is Portland cement, water, and aggregate. The principal factors in concrete strength are the water cement ratio and the extent of hydration. The extent of hydration is time and temperature. Okay. I just think I saw an article a year or 2 years ago. They actually finally found a spot in the Hoover Dam where 100% of the hydration was completed in the cement, in the concrete. Okay. Concrete will cure for a really long time as long as it's hydrated and there's adequate temperature. Okay. And the water cement ratio is low. Between those three, this is what is the main focus and how our concrete strength will be. We are finally done. So that's Learning Plan 3 lecture.